And so Pierre kind of stole my thunder. He already thanked the organizers. But we can do it again. So there's Alessandra. There's Brian.
Oh, here's Cornelia.
There's Brian. There's Cornelia. Mladen is also. We should thank Mladen too.
Yeah.
Okay. So let's thank them for a great week. Hi, Roman, you just saw this talk 2 weeks ago. Same slides.
No, I had to leave earlier from the conference.
Ah, okay. I'm
My
sorry.
first time.
If you were in Munster 2 weeks ago, am I not on? Am I on now?
Probably.
Yes.
Okay. Okay, good. Okay, yeah, so, right, this is joint work with Kai-Uwe Books and Peter Smillie, parts of it. And I'm going to talk about the borders of outer space. So I'm going to start with something that we all had to learn before they would give us a PhD, which is Poincare duality. So here, if you start with a closed, this is Poincare duality, right? So if you start with a closed orientable d-dimensional manifold, then we all know that Poincare duality tells us there's a duality between the cohomology of the manifold and homology in the complementary dimension. So this is a conference on, there's groups in the title somewhere, so we're really interested in particular in aspherical manifolds. So if the fundamental group, if pi is the fundamental group of the manifold, if the manifold happens to have a contractible universal cover, then the cohomology of M is an invariant of the fundamental group. So that's one way to define the group cohomology and homology. And so this Poincare duality tells us there's a duality between the cohomology, group cohomology and homology of the group. If you look at the universal cover M tilde, well, that's probably not, quite likely not compact anymore. But Poincare duality doesn't really care. If you look at Hatcher, for instance, how you prove Poincare duality, you prove it by looking at cohomology with compact supports. And the actual theorem is that if M is that the cohomology with compact supports is equal to isomorphic to the homology in the complementary dimension. Now, I was assuming my M was contractible. So in particular, a contractible manifold doesn't have a lot of homology. It's just got homology in one dimension. And the Poincare duality is going to kind of flip that dimension with cohomology with compact supports. So you'll get a Z in dimension D, where D is the dimension of the manifold. Okay. So Bierry and Ekman generalized this whole picture where if you have a group that acts, so here our group pi acts on its universal cover by deck transformations. All you need actually is a discrete group that acts freely and co-compactly on some contractible space X. I should highlight Bierry and Ekman here. Right. So if you have a discrete group acting freely and co-compactly on a contractible space X, if you have this condition about the cohomology with compact supports, right there, in a slightly modified form, all you need is the cohomology with compact supports is 0 except in one dimension, where it's supposed to be torsion-free. Then you also get a duality between homology and cohomology. Namely, the cohomology of gamma is isomorphic to the homology in the complementary dimension, except you now have this, you have to tensor your whatever module with this module you just made D. And you say that, in this case, you say gamma is the duality group. So that's if you have gamma acting freely and co-compactly on some contractible space X, But it turns out that in fact you can say something even if the action is not free, as long as you have a proper action. Then, of course, if you have a torsion-free subgroup of finite index, it acts freely. And if you have this condition on the cohomology with compact supports, you get that this torsion-free subgroup of finite index is a duality group, in which case it turns out that, so you say that gamma, the whole group, is a virtual duality group. So you may have to pass to a subgroup of finite index, but you get some form of duality. Okay, so we just saw, well, the last talk was really appropriate to see just before this talk. So Borel and Serre used this criterion, getting a proper action, a proper co-compact action on a nice space to prove that arithmetic groups and S-arithmetic groups are virtual duality groups. Hare and Ivanov used this strategy. That's Borel and Serre. Hare and Ivanov used this to prove that mapping class groups are virtual duality groups. And there's a group that I like, a group of outer automorphisms of a free group, and Bestvina and Feighn use this strategy to prove that the group of outer automorphisms of a free group is a virtual duality group. So in order to do this, they all needed to find proper co-compact actions on contractible spaces. And then, so they had these are important things. They need to be proper, they need to be co-compact, the spaces need to be contractible, and then they needed to compute the cohomology with compact supports of these spaces. So for all of these groups that I just mentioned, there were contractible spaces hanging around with proper actions on them by the groups. Here they are. For the general linear group, you can take the symmetric space, the SLNR mod SON. I'm talking about GLN acting, so I have to multiply by determinant. For the mapping class groups, you have the Teichmüller space, with contractible space with a proper action. And for out of Fn, you have something called outer space, which we've seen a lot about this week. And in fact, I picked these particular groups. They're closely related. The mapping class group, at least if S is positive, if there are some punctures, then the mapping class group is just a subgroup of out of Fn. And the natural map, which takes a free group and abelianizes it, induces a map on outer automorphism groups. So there's a map from out of Fn to GLNZ. And there are also natural maps from the Teichmüller space of a punctured surface is a subspace of outer space. And there's a map which is a kind of a period map from outer space to the symmetric space. And mod SG acts on Teichmüller space, out of Fn acts on Xn, GLNZ acts on Hn, and these maps are equivariant. Okay? So all of these questions about general linear GLNZ mapping class groups and out of Fn are related. You often try to prove things about one kind of group in the family by looking at what you can do for other kinds of groups in the family, and sometimes exploit these maps. So for n equals 2, this picture is really simple. The groups, if you have a punctured torus, then mod S11 is isomorphic to out of F2, and that's isomorphic to GL2Z. And the Teichmüller space is isomorphic to outer space, is isomorphic to the symmetric space. Now those who know a little bit about outer space know that I'm lying a little bit here. Here I'm really looking at reduced outer space, by which I mean that I'm not allowing graphs with separating edges. In which case I really do get all these spaces are exactly the same thing, same actions, and they're all, of course, the upper half plane, which we've seen at least in 2 other talks today, including the last one. So imaginary part of z is equal to 0, and abcd dot z is az plus b over cz plus d. And multiply it by the determinant if it happens to have, if I'm talking about GL2z. Okay, so this action is free except at 2 points. Well, it's not free at I and at omega, which is 1 plus the square root of 3I over 2. But otherwise, it's free. Of course, it's also not free at any of the orbits, any point in the orbit. So the action is free. And the quotient is the famous modular curve. And as was pointed out in the last talk, this is not a co-compact action. But if you remember what we wanted up here, oops, where did we want it? Berry and Ekman wanted us to have a free contractible co-compact action. So we don't have a co-compact action, so these spaces aren't quite good enough for us. We would really like to have a co-compact action. So the obvious first thing to try to do to fix this is to stick on a point at infinity. Then we have a co-compact space, compact space. And in fact, this is what algebraic geometers like to do because they want to understand this space, the modular curve, using algebraic geometry, so they would like it to be a projective variety, which it's not because it's not compact. But if they put a point on it, they can prove it's a projective, if they compactify it, they can prove it's a projective variety, so they get this, the modular curve is a quasi-projective variety, which was mentioned in the first talk today. Okay, but so when you add this point at the cusp, upstairs you get a point at infinity, but you also get a point, you've added a point at every single rational number. And the action extends by the same formula as before, but the action is no longer proper because if you take the matrix, for instance, 1x 1 1 0 1, it moves everything to the right, but it stabilizes infinity. So right, so the action is no longer prip. That's the whole subgroup it generates fixes infinity, and that's an infinite cyclic subgroup. Yeah, so this is not good. The action is no longer proper. And also, something else that makes us unhappy is that the quotient, we've changed the homotopy type of the quotient. It used to be contractible, now it's a two-sphere. So if you're interested in things like the cohomology of these groups, which we're supposed to be because that's the conference we're at, then you're unhappy because you've changed the homotopy type. Okay? So the thing to do instead is add a whole line at infinity. It's obvious in this picture how to glue it on to what was there before. And now the stabilizer acts, well, the cyclic group acted by moving everything to the right. It can move everything on the line to the right. And that looks much better. But of course, you have to do this equivariantly, so you also have to add a line at every rational point, which is maybe harder to see. Okay? But it's easy to see what happens in the quotient. That line up there just becomes a circle. And, right, I don't want to add a page. I just want to add a circle here at infinity. Okay, so this is the idea of the Borel-Serre bordification, compactification of the moduli space. Upstairs it's called a bordification, downstairs it's called a compactification. And Borel and Serre generalize this, and so that you can do it to any arithmetic and S-arithmetic group in the place of SL2Z. And what they did is they took symmetric spaces and they glued on a Euclidean spaces. And then they showed that the action always extends. And after you glue on all these Euclidean spaces, you get something that's co-compact. So for SL and Z, acting on the symmetric space, this bordification you get on by gluing on a Euclidean space, and you glue one on for every flag of subspaces in a vector space Q to the n, an n-dimensional rational vector space. Every time you have a flag of subspaces, you're going to glue on a Euclidean space. So in particular, in our picture up here, we glued on a line at every rational point. Well, the rational points are the slopes of proper subspaces of Q squared. Okay, so we glued on a line for every proper subspace of Q squared. In general, you have to glue a Euclidean space every time you have a flag of subspaces. If you've got a two-dimensional space, then there aren't so many flags. The subspaces have to be proper. So they proved that after they do this, you get a manifold with boundary. And furthermore, the boundary has the homotopy type of the Tietz building of subspaces of Q to the n. So this is the Solomon-Tietz theorem, then says that this boundary is homotopy equivalent to a wedge of spheres, which we also saw in the last talk. I could have probably cut out the whole first 10 minutes of my talk. Right. The dimension of the symmetric space is n times n plus 1 over 2 minus 1. This is a wedge of spheres of dimension n minus 2. Hn bar is a manifold with boundary. Point grade duality looks slightly different for manifolds with boundary, but not too much different. You still have the duality between cohomology with compact supports and homology, but now you have to look at homology relative to the boundary. But in our case, the boundary, the symmetric space, is contractible. So by the long exact sequence, of a pair, this is just the homology of the boundary, since that's contractible. So you get that the cohomology with compact supports of this space is the homology of this wedge of spheres. So it's free in one dimension and it's zero otherwise. And the dimension is n times n minus 1 over 2, which is easy to calculate. So in particular, this is exactly what Bierry and Ekman asked us for. They asked us for a proper action on a contractible space with so that the cohomology with compact supports was 0 except in one dimension where it's torsion free. Okay, so we conclude that GLNZ is a virtual duality group. Okay, so that's what Borel and Serre did. Now, Dan Grayson came along and he kind of was more in the spirit of the last talk. Instead of adding a circle to the modular curve, you can also think of just cutting off the cusp, eliminating the thin part. What you get looks exactly the same, right? You either add a circle at infinity or you chop off the cusp and the boundary is now a circle. So upstairs, what happens? Instead of adding this thing at infinity, you've cut off something. So this is the picture we saw in the last talk. You cut off something towards infinity, and you also cut off horoballs around every rational point to do it equivariantly. And the result, what you get, is homeomorphic to the Borel-Serre bordification. It's just there are a lot of things that make it easier to understand. One is you don't have to worry about extending the action. You don't have to worry because you just restrict the action. You cut out something equivariant. Yeah, you don't. It turns out the contractibility proof works here too. There are various contractibility proofs that just work here. You don't have to worry about what happens when you've added something at infinity. You know, you need a collared neighborhood and all sorts of stuff. So Grayson did this for SLNZ and SP2NZ, and yeah, it's been done for other arithmetic groups as well. And I forgot to write down the reference. Does anybody know who I should write down?
Paper?
Maybe? Okay. Who? Yeah. Saper. Okay. And I should say that Bartels, Luke, Reich, and Ruping proved the Farrell-Jones conjecture for SLNZ, and they used Grayson's description of the Borel-Serre bordification to do what they did. Right, so let's get to out of Fn. Out of Fn, Bestvina and Feighn also did something very similar, motivated by Borel and Serre. They took outer space and added some stuff at infinity and proved that the cohomology with compact supports of what they got was free in one dimension and 0 in other dimensions. There's some subtle points here that have to be addressed. So the way we proved that the cohomology with compact supports of the bordification of the symmetric space had these properties is we used Poincare duality to identify it with the homology of the boundary. Well, outer space isn't a manifold, so you can't do this. So, but we still get, they can still compute the cohomology with compact supports directly. And so yeah, so what am I going to do if they already did this? So this is what I want to talk about. Whoops. Don't want to cross this out. I want to emphasize this. So what we did is we kind of followed Grayson's lead. Instead of adding stuff to infinity, we're going to cut something away from infinity. So we're going to define an equivariant deformation retract of outer space. We're going to show that it's homeomorphic to the Bestvina-Feighn bordification. So we could just quote their theorem now that this space is highly connected at infinity. But it turns out that this description is a whole lot simpler than what they did, and we can make the proof a whole lot simpler. And not only that, but it gives us a lot more information about what this bordification looks like than you got from their proof. We can show that the boundary of this bordification is covered by contractible spaces, kind of like the Euclidean spaces that are at the boundary of the Borel-Serre bordification. And they intersect in contractible spaces. So you can look at the nerve of this cover, which is what Borel and Serre did for the symmetric spaces, and they got that the nerve of this cover was Tits building. So we don't get a Tits building. We get but the nerve of the cover we can identify with a subcomplex of a sphere complex of spheres inside of a certain 3-manifold. And so that's kind of a natural analog then of the Tietz building for the free group. And we can also say exactly what the wall stabilizers are, and if I have time, I'll explain. I won't have time. We're all tired. So these wall stabilizers, yeah, are groups that we've studied before, and their cohomology of these stabilizers is related to the cohomology of out of Fn via assembly maps, which some of you may have heard me talk about before. Anyway, so that's what we're going to do. Right. So let me just tell you how you make this space. The description's kind of pretty. So first of all, the outer space is a space of metric graphs marked by isomorphisms. My metric graphs are are all finite. They've got no separating edges, no bivalent vertices, and the sum of the edge lengths is 1. But yeah, it's a space of metric graphs marked by isomorphisms. So for n equals 2, there's just 2 kinds of graphs. There's this one. I've eliminated all graphs except those kind for n equals 2. And the whole of outer space decomposes as a union of open simplices. There's an open simplex for each possible graph, each possible marked graph. So for n equals 2, the decomposition of the outer space is the familiar Feighn tessellation of outer space. You get there's a marked theta graph, gives you an open triangle, and a marked rose gives you an open, actually I don't want that one, an open line, one simplex and a 2 simplex. The reason that there's 2 different things is the marking is different. So if A and B is my fundamental group, then maybe in this graph A goes around this way, in this graph A goes around this way, whereas in this graph A goes around this way and B goes around that way. So they're the same graph with different markings. And I go to a boundary of the open simplex by collapsing some edge. So there's 3 different edges to collapse. I can't collapse 2 edges, or I go beyond outer space. I get out outer space. Okay, so that's the basic picture of what outer space looks like, at least for n equals 2. But instead of this picture in the hyperbolic plane, it's very convenient because you can fit all of the triangles in outer space into a little circle. But I prefer to give simplices a Euclidean metric. So remember, the sum of my edge lengths was equal to 1. So that corresponds to a Euclidean triangle. A plus B plus C equals 1. And I'm going to label the faces of my triangle by the various edges. So there's an edge A, an edge B, an edge C corresponding to these 3 points. And I'll call this AC, call this BC, and call this AB. So I'm going to label faces by subsets of the edges. So that's my picture of a simplex in outer space without the marking. So I'm going to make, so that's outer space. I'm going to make cells by taking these simplices and cutting off parts of them, okay, the parts that I don't want. And so to understand which parts I'm going to slice off, I need to tell you what a core subgraph is. So a core subgraph is just a subgraph with no separating edges or isolated vertices. So for example, in these, if these are the graphs, what are the core subgraphs? Well, this guy, whoops, that guy is core. That guy is not core because it has a separating edge. This guy is core. So is this one. Core graphs don't have to be connected. This guy is core. They could have bivalent vertices. This graph is not core because it's got a separating edge. So I'm interested in the core subgraphs. And the instructions for constructing my cells are, I'm going to shave off the faces opposite core graphs. So here AB is a core graph. So there's the AB face. I'm not going to cut that off. I'm going to cut off the opposite face. BC is a core graph. and AC is a core graph. So I cut off all those faces, and I'm left with this. So starting from the simplex, this is sigma of GG, I'm left with something I'm going to call J of G. Okay? I'm going to do a couple more examples. If I have rows, so both, there's two subgraphs, they're both core. A is a core subgraph, and I cut off B. B is a core subgraph, and I cut off A. So the, yeah, I'm left with that. In fact, no matter what rows I have, every single subgraph is a core subgraph, so I'm going to be cutting off every single face. So, for instance, here I'm going to cut off that, that, that. And when I cut off a higher dimensional face, I want to cut it off less. So I want to cut off that, 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 but I want to cut it off less. And what I'm left with is a hexagon, and that's my joule. Yeah. So this is a standard way of constructing something called the permutahedron. You take a simplex, you shave off every face, you shave off the edges, the vertices a lot, you shave off the edges a little bit less, the two faces a little bit less, etc. And what you're left with is the permutahedron. It's got one vertex for every permutation of the letters A, B, and C. So that's why it's called a permutahedron, I guess. Okay. In general, it turns out, so for any rows, this is what you get. This cell I'm constructing is a permutahedron contained in the face, in the simplex. And here's a proposition. If you have any marked graph, then this J of GG is a convex hull of the permutahedra contained in the rows faces. So I have a very good concrete description of what the vertices of my eventual retract are. It's going to be a cell complex. The cells are going to be cells, these J of Gs, and the vertices are going to consist of a rows, a marked rows, and an ordering on the edges of the rows. So let me just do an example here. ABC. Yeah, what are the rows faces? Well, they're all of the one-dimensional faces are the rows faces. And each of those has a permutahedron in it. And if I take the convex hull of those guys, this is the same picture I constructed earlier by saying I'm chopping off the core subgraphs, the faces opposite core subgraphs. It's just another description of the same thing. And let me do one more. Yeah, one more. In this graph, what are the rows faces? Well, if I collapse B, I get a rows, so that would be over here. B equals 0. If I collapse C, I get a rows, that would be over here. In each of these rows faces, I have a permutahedron. And now I'm supposed to take the convex hull. Okay, so there's my my cell. Okay? So now you can understand why we're calling them joules, maybe. They kind of look like facets. Okay, yeah, one more. Oh, I'll just take the convex hull of the rows faces. Yeah, there it is. Okay, so I have my outer space decomposed as a union of simplices, of open simplices, and I've kind of chopped off lots of pieces of these simplices, and then they just fit together in the opposite way. We've seen that for n equals 2, these joules all look like that. Whoops. They look like hexagons. Etc. And you can see what I'm getting. Whoops. Well, maybe you can see what I'm getting. Yeah. Well, I'm going to get that. All the jewels are all the stuff inside. It's the thin part of this picture. Right. And the theorem is that this is an equivariant deformation retract of outer space, and out of Fn acts properly and co-compactly. Properness is no problem. Co-compactness is also no problem. Right, so that's exactly what I wanted. Right. And then there's also another theorem that shows that this is actually homomorphic to the Bestvina Feighn bordification. And in order to explain that, I would have to tell you what their bordification is, but I'm not going to do that. And one advantage, as I said, of this picture is, well, first of all, it's a nice simple picture of what the bordification is. Second of all, it's the proof that this is highly connected at infinity, which is what you need to calculate the cohomology with compact supports, turns out to be much easier than the previous proof. So, and uses combinatorial arguments similar to the original Vogtmann paper where we introduced outer space. But what I really wanted to tell you about in the last 5 minutes is what the boundary looks like. Why this gives you a picture of what's in the boundary. So let me spend the last few minutes talking about the border of this retract. So it turns out that to understand the structure at infinity, it helps to use a different model of outer space. So instead of whenever I have a marked graph, I can instead think of a marked graph as a system of spheres in a 3-manifold. So how do I do that? Well, I just take this graph and thicken it up to a handle body. I'll do it there and there. So thicken. And then for each edge in my graph, I'm going to see what happened to each of these points. In the middle of the edge became a disk. And now I'm going to double this whole thing, which is harder to draw. And I get a collection of 2 spheres in my handle body. Now, theorem of Laudenbach tells me that this diagram commutes up to homotopy in an essentially unique way. So then, so I can lift this G to a G tilde, and then I can pull back my spheres, my pretty spheres, in the upstairs handle body back down to this handle body, and they'll all get all messed up. But there'll still be a disjoint collection of 2 spheres. Okay? And it turns out that there's a one-to-one correspondence between marked graphs and collections of 2 spheres in a doubled handle body. So instead of thinking of marked graphs, I now want to think of 2 spheres in a doubled handle body. And in this picture, what does a core subgraph correspond to? Well, it corresponds to a subset. So here's my, if here are my 2 spheres, I'm only going to draw half of them because I can't double. They correspond to some subset of edges, right? So that some subset of spheres So if C is my core graph, in this case it's that core graph, corresponds to those two spheres, and there's another sphere left over. Now if I take my handle body and cut it open along that leftover sphere, then the fact that sigma is a core graph means that it's not supposed to have any separating edges. That means that none of these spheres, when I look at them in this cut open guy, none of those are separating. That corresponds exactly to the core graph doesn't have any separating edges. So anyway, I can interpret core graphs in terms of sphere systems. If I have a core graph, then what's left over doesn't fill the manifold. Yeah. I'm worried about time. I'm not going to belabor this point, but let's go back to our joule. So the joule was obtained by shaving faces opposite core graphs, or thinking of core graphs shrinking to zero. So the face opposite a core graph means the core graph is shrinking to zero. So a core graph has fundamental group. It's a subgraph, doesn't have any separating edges. It's got to have some fundamental group. So when you shrink it, you go out of outer space. You go beyond outer space. And here's the proposition. The face opposite a core graph is isomorphic to a product. So here BC is a core graph. Whoops. BC is a core graph. There's BC. The face opposite the core graph turns out always to be a product. J of BC, the joule for BC, which is just going to be a line, and the joule for a graph you get by collapsing the core graph to a point. And in terms of sphere systems, this thing that you get by collapsing a core graph to a point, well, that's just two spheres that aren't in the core graph. In order to get the whole graph, you have to put in all the spheres. But if you just look at the guys that are not in the core graph, that's just two spheres. It doesn't have anything to do with the graph you started with. It's just two spheres in this handle body. So it's independent of the graph you started with. So this J of G mod n, the notation's a little misleading. It doesn't depend on the graph you started with. It only depends on the core graph, turns out. Right. So let me see how to say this. I want to show you what the boundary is made of. So if you think about it, you take a maximal simplex, and I look at all that corresponds to a graph or a sphere system, and I look at the core graphs. I've shaved off all of the core graphs, and I've got a panel. And what this proposition says is that what I get is, yeah, what am I saying? What am I saying? Trying to say it too fast. Yeah. Every time I have a sphere system that doesn't fill up M, then there's a core graph somewhere. Then I can fill it up with in lots of different ways by things that will give me core graphs in the resulting thing. So if I start with this guy that's this sphere system, which doesn't fill up the 3-manifold, I can complete it in lots of ways, and every way of completing it, I can look at a core graph inside there that will give me a facet of a joule. Okay? So for every one of these systems, I have lots and lots of ways of, I can cut open my manifold along this set of spheres and look at all possible ways of adding more spheres to get a graph. And each of those graphs will give me a facet of a joule. So each of these graphs gives me a panel. They all fit together, and the claim is that together all of these facets corresponding to this particular set of spheres, which is not in, which doesn't fill the manifold, gives me a wall. And the theorem is that all of these walls are contractible, and every non-empty intersection of walls is contractible. And the proof is to show that these walls are isomorphic to the complex of non-separating sphere systems as in M minus this subset of spheres delta crossed with some finite joule. And there's a standard surgery argument to show that sphere systems like this are contractible. So I've got my boundary of of this bordification decomposed into a union of contractible pieces, and I know exactly what they look like. They correspond to complexes of spheres in this doubled handle body, and they're contractible, right? So yeah. So the nerve of this cover, I get one of these guys for every set of spheres that doesn't fill my handle body. And yeah, I think so. You can also the dimension of this guy is 2n minus 4, and the fact that it's highly connected at infinity means that it's 2n minus 5 connected. So actually, this sphere system is homotopically equivalent to a wedge of spheres. So it's kind of the analog of the Tietz building. Yeah. I'm supposed to stop. Yeah.
Could you just say, you probably said it already, but could you say again why core subgraphs are not supposed to have separating edges? Because I can imagine contracting a whole, any homotopically sort of non-trivial subgraph and sort of heading off to infinity by contracting that subgraph to.
Right.
What happens?
Why am I not using separating edges?
Yeah.
This nice theorem that so first of all, if I don't have a separating edge and I collapse some edges, I'm not going to create a separating edge, right? So collapsing edges won't affect this property. I won't have this nice description of these jewels as the convex hull of the permutahedra in the row spaces. So I won't have a nice description of what the vertices of my space are, of my bordification. I have a description of the bordification as a union of cells. I can tell you exactly what those cells are. I can tell you exactly what their vertices are and what they look like. And if I allowed separating edges, the description just doesn't work. That theorem isn't true. That proposition isn't.
Could you tell me what happens in the case that I just... So suppose I take a subgraph which has a separating edge in it, but it's homotopically non-trivial on both sides, like the example, and now I collapse that guy.
Yeah.
Where do I...
You stay inside outer space if you just collapse that edge. You don't go out.
No, I'm not just collapsing the edge, I'm collapsing the whole subgraph.
Okay, but you could first collapse the edge.
I could do, yeah, that's right.
And then you would be back in...
yeah.
then
I see. So I would still go. So I would still end up in your bordification. Just
you would still
do
end
what-
up in
you
my
just want me to go there
bordification.
a
I just
particular
want you
way.
to do it
Yeah,
this
okay,
way.
Right. Okay.
Yeah,
Okay. All right.
exactly. Robert.
Have you thought about what happens in the case of mapping class groups? Let's say you have to take a surface and you look at arc systems,
Right,
and then
same thing.
taking what you're doing, you're saying don't take separating arcs. And then when you look at simplices,
There's a complete translation in that case. If you, yeah.
So what happens? Does it differ?
So this is
completely from
actually-
Harris?
I'm pretty sure. Yeah. So Hare doesn't use, does Hare use separating arcs?
He doesn't care whether they're separating or non-separating.
Yeah, okay.
He just looks at these.
So this description would work if you don't allow separating arcs. And there's no reason to put separating arcs in there.
I was just thinking, like, when you take these core graphs.
Mm-hmm. They don't have separating arcs.
Yeah.
So incidentally, I discovered last week that these joules that I've been constructing are something that the physicists have been talking about for a while. They call them Feynman polytopes. And the structure of and they call core subgraphs one particle irreducible subgraphs. So somehow this notion of not having separating edges is useful in other contexts. But yeah, so I'm sure you could just translate this directly to the. So yeah. Yeah, so I think Hare doesn't exclude. I can't remember whether he uses separating arcs or not.
Simple. I just wanted to know, when you talk about these walls, these are analogs of the horospheres, basically?
Yeah,
Is that so
they're
that
analogs
you
of the
know
horospheres, of the Euclidean pieces that you glue on to a symmetric space.
So they're made up of these spaces of the jewels, but they connect and form a...
Right. So that each of these guys, each of these facets of a jewel is a panel in the wall, and the panels all fit together to make a wall. Yeah. So yeah, I was thinking of. I think in one talk recently, I did give the title "Walls at the Borders of Outer Space," but I was kind of afraid to do that. I'm going to Mexico. Maybe I shouldn't give that talk there. Keep the aliens out, you know, the stuff is beyond outer space.
Who's paying for these walls?
Yes, exactly. Aliens. Yeah. Anyway.
No more questions. Okay, so let's thank Kai-Uwe again.